All right. So yeah. So since we didn't record that session, so I thought that I'll kind of start from that and then move on to the newer topics. So before we start with leaderless, a quick overview of why we are moving to that architecture, right? So if you look at single leader replication architecture, it's pretty easy to understand. There are no conflict resolution, issues around it. But then when you get into fault tolerant, networks, and you want to have different consistency models to support, and you want to take care of network partitions and all those issues, then I think things get challenging, and that's where multi-leader approach comes in. But it has its own trade-offs. So the next, architecture that we look at to kind of alleviate or handle the challenges in these approaches is leaderless, right? Uh, Also, the other thing you would notice in both of these earlier approaches is that the leader node kinds of becomes a bottleneck, right? Whether it's single leader or multi-leader. Um, you are bottlenecked both in terms of handling failures, but also how do you propagate rights to your followers, right? So there are challenges around it. So to alleviate those issues, one of the approach is leaderless replication, right? And the idea is you want to allow any replica to directly accept rights from the clients, right? The idea has been there in research since 1970s, but for all practical purposes, it became popular after Amazon adopted it. And there are these commercial systems which are using this architecture. So let's look at an example and to support this model. So for example, here in this picture, they are showing that this first user on the top is sending a write request, and it's a 3-node system. So it's sending a write request to all 3 nodes. And what happens is the third node is down, and the data is only propagated or written to 2 nodes. Now later another user comes in, and again the read request is sent to all 3 nodes. Now first of all, even before that, right, if you only send a read request to one, let's say a random node, then it's a problem, right? You may not get the latest value. But even if you extend that model and you say that, all right, I'm going to send my read request to all the 3 nodes, um, in that case also, there is a possibility that you will get a stale value from one node and you get the most updated values from the other nodes. Feel free to interrupt me if there are any confusions or if I'm going fast. So that's the challenge here, right? You are getting stale versions of data from some nodes. So the question is, how do you kind of detect it? And a simple solution is like you use versioning and you say that, okay, I'm going to send read request to all nodes and then compare whichever is the latest value, I'm going to pick that. So this is a very simple scenario, but what this scenario really highlights is that this is leading to 2 questions. One is, this is a 3-node system. So when I send a write request, right, how many nodes should I wait for, right, before confirming that my write was successful? So this is a 3-node system. It's a pretty small cluster. It seems like I can wait for all the nodes. But if it's a 100-node cluster, you don't want to wait for all 100 nodes to confirm that the write was successful. And there can be failures on some of the nodes. So how do you maintain a trade-off between latency and consistency, right? That's the big question there. And the same question is there for read, right? You send a read request to all nodes, but how many nodes should you really wait for to receive an acknowledgement? That's like these 2 things form question number 1. The second question is that we talked about stale values here, right? This node is returning a different value than the other ones. Then the question is, how do you identify stale values and how do you actually fix those values? Because if you think about overall distributed system, the overarching goal is that you want to keep your replicas in sync, right? Um, to maintain this trade-off between latency and consistency, you are kind of saying, all right, I may not have all the replicas in sync all the time, but I want to keep them in sync as much as possible. So this actually example really branches off to two directions. One is the idea of quorums, right? The other is how do you handle entropy in the system? How do you handle then that replicas are not in sync, right? Um, so touching on the first topic right here, what do we mean by quorum consistency? So there are two concepts there, write and read consistency. So you want to say that, all right, I have n nodes in my cluster, but I only care about these W nodes to confirm that my write was successful. As long as I have an acknowledgement from them, I'm going to move forward with that. Similarly, read consistency. You don't want to wait for all the end nodes to respond. So you have a number defined that says, all right, I'm good with this, read acknowledgements. And one of the rules that's followed in distributed systems is this one, that you pick these numbers about W and R in such a way that it's always greater than your total number of nodes in the cluster. And we'll see why that's the case. But this is in general, the idea of quorums and these write and read consistencies. Does that make sense?
Yes. Yeah, that makes sense.
So now coming to that, why is this rule relevant, right? So if you look at this figure here, essentially the quorum condition, it does two things. First of all, if out of n nodes, some nodes are unavailable, then how do you ensure that your system is not blocked and it can still process reads or writes? That's goal number one. And the second idea is that when you try to read data, for example, in this case, how do you ensure that you are reading the most recent value? So this is an example to illustrate that. You have a 5-node system. So your N is 5, and they have taken W as 3 and R as 3, right? So again, W as 3 means I need confirmation from these 3 nodes, which is 1, 2, 3 here, to confirm that my write is good, and similarly for read. So as it's shown here, the idea of this equation is that you should have an overlap between these write nodes and read nodes, right? To make sure that you have at least one node which has the most recent value, right? So that's essentially basically taking care of the second point, that you want to pick the most recent value during reads. I have given some other examples. So let's say you look at the second scenario where you're setting write to 1 and read to 5. So the equation will still be satisfied, right? 1 plus 5 greater than 5, and there is an overlap there. What do you think would be the pros and cons of setting these consistency levels? Like if I set write to 1 versus a higher number.
So if you have a lot of writes, then you would want the W to be lesser so that your system is available. If you have a lot of reads, then you will want R to be less so that your reads are always available.
So when you say, can you elaborate on, so I think you touched upon both these cases. So if we first look at the second one right here, like writes is 1. So you're saying that by doing that, we are making writes more available?
Yep, because you want only one node to be available for
Right.
your write to success, right? whereas your read will be less available because you would need 5 nodes, like all of the nodes to be available to actually read a value.
That's right. So, and like Abhishek explained, I mean, does everybody see that point? If you only have, this is saying that I only have one node, let's say replica one, designated as my write confirmation, list. So I only write to that and I get confirmation I'm good to go. I don't need the other nodes to be available for writes. But for reads, I want confirmation from all 5, right? Before I can say, okay, read is successful. Um, yeah, that makes sense. The other thing is latency, right? If you have, you can think that you can argue in both ways. So you can say that if your write is 1 here, what if this, so your latency will be less, right? Will be pretty good because you're only waiting for an acknowledgement from one node, right? But what if that node fails, right? Then we have to handle other scenarios. Um, and that is essentially leading to the third one. A similar third example is a similar case. So I have switched that. So I'm saying that I need confirmation from all end nodes, right? Which makes it, less available because if one node is down, then it breaks that. But for read, I am only going to refer to one node. So both satisfy the equation, but I'm just giving an example of what are the trade-offs in terms of latency and availability that you would observe in each of them. Yeah, so the takeaway from this point is that why do we need quorums? Because they allow to detect stale reads. And the second thing is they allow to tolerate unavailable nodes. You don't want the whole cluster to be up to process your reads or writes. Now, the question is, this seems to be a pretty nice model about this equation. But first of all, we talked about this thing, right? What are the implications of picking different write or read values? So if you increase those values, then you're saying that you have to wait for an acknowledgement from that number of nodes, and that will increase latency. But if you decrease those values, then your consistency can be compromised, right? With, yeah, and the upside is you don't have to wait for a large number of nodes to confirm, so latency can be lower. So there are trade-offs in each case depending on your application requirements. The important thing to note here is that you should be aware what are the implications of these values. So that's point number one. The other thing is we talked about this equation, but it's interesting to see that there are cases where even this equation can break, right? And one of the cases is this idea of sloppy quorum, and the other is about handling concurrent writes. So let's talk about the first one, sloppy quorum.
Just a second, I have a question on the first part. Why would the latencies increase if we have more number of nodes to confirm read or write? Because we would be sending request to all of them in parallel, right?
Correct. But I'm thinking like, even if you're sending requests to all of them in parallel, let's say some node, network issue is there, something is slow, right? But you can't confirm a write request to be successful unless you hear from all of them. So if one is slow in responding, even though it's working, right? It's not a failed node.
Yeah, right. Okay.
So, yeah. Does that make sense?
Yeah, that makes sense.
Okay.
Yeah.
So, yeah. So let's talk about this sloppy quorum, right? So we are saying that we are choosing W and R in such a way that we always have an overlap. And now I'm making this point that you may not have an overlap, right? So what is that situation when this can happen? And the quick note there is, you are not going to land into this sloppy quorum intentionally, because if you're following this equation, then you know that you are making a decision consciously that you are making sure that there should be an overlap. but there are situations where this equation can break. So let's look at that scenario. So what happens is, let's say you have a 5-node cluster, right? And I'm going to, add this hinted handoff concept here because they go together. But yeah, so you have a 5-node cluster and you're designating the first 3 for your right quorum, right? Now let's say based on your equation, you are doing good, but in practice, let's say when you're sending a write request, that time B gets down. So what happens is, here you are faced a question, right? When one of your nodes in the replica set goes down, you have 2 choices. You can either respond to the client saying that, all right, my write quorum is not satisfied. I'm not going to process the write request. That's one way for you to go, right? The other way is that, all right, I'm not going to deny the write request. Since I have other nodes in my cluster, I'm going to use them for the time being and process the write, right? So this is the approach that I'm talking about. So if B is down, I'm going to pick another node, D, which is in my cluster. It is not a part of my write quorum, but it's a healthy node in my cluster. So I pick that to satisfy the quorum, and then the data is replicated to A, D, and C, right? But what will happen is, when you write the data to a node which is outside your quorum, you're also going to add some additional information in its metadata called a hint, since the write was originally intended for B, right? And the whole idea is that when B comes back, you want to go back to the original quorum, right? So as soon as B recovers, because D is carrying this hint information, it will attempt to forward a hint back to B. And once that hint is replayed, D is kicked off from the quorum and the original quorum is restored, which is ABC. So that's the idea of hinted handoff, right? So even though you have a quorum for your write operations, you are taking into account that in real world, things can break when you're actually processing writes. So this is one approach. Now, why is it called sloppy quorum, right? What if the overlapping node between my read and write quorum was B, right? And before I did this whole of hinted handoff and before B came back to my replica set, what if another client issued a read, right? In that case, I'm going to either get a error or I'm going to get a stale value, right? So now suddenly my quorum, that overlap nature of my quorum is broken. Does everyone like see this idea why this is happening?
So my understanding of sloppy quorum was a bit different.
Okay.
So one thing you said, so your first part, that in a 5-node cluster, we are making ABC as replicas for write, but we won't designate any like a fixed set of nodes to be for write, right? We are saying that if any three are available, we
Okay.
can do a successful write. Isn't it like that? While
Yeah, yeah. So you are saying right. So you're saying similar thing, but in a little different way, right? So so yeah, I'm designating this, but like you're saying, as long as I have 3 nodes. So if I go with the number, right, I need acknowledgement from 3 nodes, right? It can be any 3. So that's what I'm doing. I'm saying that okay, B is down. I have 2 now, but I can add 3. I can add D to make it 3. So as long as I have 3 nodes in my, right quorum, I'm good to go with it.
so okay, so
But I think,
then it is not sloppy quorum, right? I think in sloppy quorum, well, like, so according to my understanding, right? So let's say you have 5 nodes for some particular data, right?
okay,
You have other 5 nodes, your data is partitioned, and you have other 5 nodes for some other set of data. right?
Right.
Now, in this node cluster of 5 nodes, let's say you don't have enough nodes available. You don't have 3 nodes available. Because for write, you need 3 nodes to be available for write quorum. But
Right.
let's say for this data set, out of these 5 nodes, you don't have 3 nodes available.
Okay.
Then you are not able to satisfy your quorum
Correct.
condition, so you cannot perform right. So one thing you can do is you can return to the customer that I cannot perform
Yeah.
right because I don't have. Or you can go to a node cluster of other data. So that
Uh-huh.
cluster does not belong to your data.
Correct.
You will go there. There you will pick any 3 nodes which are available and write the data over there and return success to the customer. So you have stored the data somewhere for the customer. It's not in its home nodes where the data should be. You have stored it somewhere.
Right.
And later when these nodes become available,
Yeah.
then from those nodes, this data is handed off to the user.
Correct.
That was my understanding.
No, no. So this is, I'm seeing like the, I think we are still, I'm thinking we are saying the same thing. So when you said, so rather than, let's say I take out the first statement, right? Let's say I'm not designating these nodes, but what you explained is you're talking about this sort of multi data center, like approach, right? So yeah.
No, so not multi-data center. I'm saying data is partitioned. So let's say
Yeah, yeah,
my
right. Even if you have two clusters, right? 5 nodes, 5 nodes,
yeah,
right?
yeah.
So you are saying that even though you're not going with specific nodes to satisfy your right quorum, but you are phrasing it in a different way as I see. You are saying that my right quorum belongs to first cluster. Now, suddenly, because of some issue, I can't satisfy the right quorum in my first cluster. So I move to nodes in the other cluster to
Which,
satisfy my right
which
request.
which don't have the data which are not storing that data for so like so once again, so let's say my key of 1, right, was stored in the node cluster ABCDE, right?
Yeah.
And my other keys, let's say key ABCD, so let's say my keys which are numbers 1 2 3 4 5 6, they are stored in ABCDE cluster, right?
Okay.
My keys which are alphabets, which is ABCD, they are stored in other cluster, which is FGHIJK, right?
Okay.
My data is partitioned in such a way that any key which is a number key will be in this cluster. Any
Yeah.
key which is alphabet key, which is will go in this cluster, right? So
Uh-huh.
my actual data for keys which are number lives in this cluster. Now
Yes.
I'm saying and now if I get a write request for a key which is a number, then definitely if I don't have a quorum out of this
Yeah.
ABCD, I cannot store data here,
Right.
right?
Right.
So although the data is typically not stored on those nodes
Yeah.
actually don't have my data. But for some
Correct.
time, I will just keep it for some time unless my nodes are
Yeah.
down. And then later I will bring back the data. So that
Yes.
is my understanding of
So
stuff.
that is what I'm like, isn't the same thing? Like I'm saying D, let's say I'm saying D doesn't have my data. Whatever I'm trying to write to ABC, let's say D and E don't have that data. But because now suddenly I can't satisfy my right quorum with ABs, so you can drawing an analogy with what you are saying. Let's say I don't say it as a 5 node cluster. I break it into two clusters, the way you are explaining, ABC and DE, just as a very crude example. So now I'm saying suddenly my first cluster where my data that I'm trying to write belongs, and it's not B breaks, right? Then I'm saying, okay, for some reason, I cannot satisfy the quorum in this cluster
Yeah.
and move to another cluster, a healthy node from another cluster, which still doesn't store the data I'm trying to write. It's totally new to it. That doesn't matter. But I'm temporarily sort of borrowing a node from another cluster to satisfy my right quorum.
Yeah.
Then when it B comes back, I put it, kind of sync it and put it back.
Yeah. Yeah.
Isn't that?
Yeah, yeah, no, that's right. Yeah, I thought that like, yeah, and I was thinking your point was that, like, in a 5 node cluster for some data, we
Yeah.
have designated ABC as the node
Oh,
to write, and
yeah.
So I was saying, no, it's not like that. Any three nodes are okay for my write to succeed.
Right, yeah. Sure.
No, actually, my understanding is a little bit different. I mean, I work, so I worked on Cassandra. So there, it's a little different. So hinted handoff actually works only when the quorum is met, but you still couldn't reach that replication factor. So there can be multiple nodes in the cluster, but replication factor is can be 3 or 5 or something like that. So when you are saying that that quorum rule W plus R greater than N, that N is that replication factor, not the total number of nodes in the cluster. So when you are trying to write a value to a particular key, you have to write it to a specific nodes itself. That is how that hash ring and everything works. So so if the replication factor is 3, but the corresponding 3 nodes that you have to write on doesn't exist, so you will write it only to let's say the right quorum is 2 and the replication factor is 3. So you will try to, you don't have you have only 2 nodes. Right quorum is met, so you can't fail that right. So you instead write to the 2 nodes, and you actually store a hint in the coordinator itself.
Okay.
So when the corresponding node that comes back, you actually say that this is a hint stored for you. You write it down, something like that.
But the replication factor is how many number of nodes we have in the cluster, right? So if we have 5 nodes, then 5 is my replication factor.
I mean, you can have 100 nodes, right? You can have hundreds and thousands of nodes, but you won't store that value thousands of times, right? So you will actually store it only 4 or 5 times or 7 times, something like that. That is much lesser than the total number of nodes in the cluster.
Yeah, you are saying about data partitioning, that out of 100 nodes, I have partitioned my data that, let's say, 5 nodes will be used to store some data, right? So the replication factor is 5.
No, I think what he's saying is even not even getting into partitioning, but what, if I understand this right, it's like you have like 100 nodes and you are saying for some reason I'm only going to, even if the whole data set, right, not the partition one, I don't know who was speaking earlier, but I think what you are saying is if you only want to maintain replication of 10 out of 100, then you are having your whole data set replicated on only 10 nodes out of 100, and that's your replication factor.
Yes. So now, according to your point, you are saying that, let's say if my replication factor is 10, and although my right quorum is met, but unless I'm not able to replicate in all of the 10 nodes, I will say that it's a sloppy quorum, and I will.
No. That's not. I'll maybe let. I don't know who was speaking earlier.
I think Uday was speaking.
Yeah. So do you want to? So maybe let me phrase it the way I understand, and then you can point out where things are missing. So based on what we are saying now is if replication factor is 10 and n is 100, right? But my right quorum is not 10. Let's say my right quorum is 5, right? Or my right quorum is 6. So out of 10 nodes, I'm saying that as long as I satisfy 6 writes on 6, I'm good. And my read is 4, or 5, then that is good. But now the sloppy quorum is basically the idea where out of those 6 nodes, right, that I define for my right quorum, let's say I can't reach one node, then I am going to pick one node outside my okay, this is interesting. So should I pick the other healthy node from outside my right quorum, which is like 10 minus 6, which is like the rest of the 4 nodes? Or should I go out of my replication factor? I can't really go out of my replication factor. Right?
So you are saying that out of, you had total 10 nodes,
No, I
and
have total 100 nodes and my replication factor is 10.
And replication factor is 10. So you would be storing the data in any of the 100 nodes as long as your replication factor is met of 10. Is it like that?
No, no, no. I'm saying if I have 100 nodes and my replication factor is 10, then I should be storing, I should have 10 designated nodes, right?
Right, for that data. Yeah.
Yeah, right. And then within that 10 nodes, I have a write quorum set as 6.
Yes, right.
And then my read quorum is set as 5.
Yeah.
That means there is an overlap of one node.
One node, yeah.
Now, when I'm sending a write request, if one of the nodes fails, right, where I'm sending for the write quorum. So suddenly, instead of 6, I only have 5 nodes available for my write, which doesn't satisfy my write consistency.
So one question here. So you had, you needed total 10 nodes to write. So out of those, out of them, if as long as 6 are available, you can do the write, right? So now you're saying you only have 5 nodes available out of them. Is that what you're saying?
Yeah. Yeah.
Okay.
So if I only have 5, I cannot satisfy that request by the definition. Yeah. So what I do is I can pick one healthy node, which is not in my set of 6 nodes, right? I can, now where I'm getting confused is this new node that I pick up, I can either pick it from the, rest 4 nodes within my replication, cluster.
But that's what we said, right? That they are not available. So how will you pick them?
No, I think they are available, but
they're available.
But I think the point I did not get is like, this is not a fixed node, right? The number is fixed, but the nodes that we write to are not fixed, right?
Correct.
It's like 5.
Exactly.
So as long as the other 4 are available, it's like they are available. It's not like, So
if it's not a fixed node, then I don't know how it works. Because we have 100 nodes, right? If it's not a fixed node, then every time people go and they can write to different node or read from different node.
No, we are not looking at 100, right? We are looking at, let's say, 10 out of 100. 10 is your replication factor.
So for out of 100, to answer Leon's question, I think out of 100, these 10 nodes are fixed or picked for that set of data. I mean, like that is a partitioned data.
Yeah.
So you always have that 10 nodes. The other 90 nodes are for different set of data.
Different set of data. Yeah. And out of that 10, if any 6 are available, so you have not fixed any 6 of them. If any 6 are available out of 10, then you can perform the write.
Right. Okay. And let's say if 6 are not, let's say if, okay, now I say only 5 are available, right?
Yes.
Then I jump to outside my.
Yeah. Right. So although you don't store the data for those nodes in other out of those 10, but in this case you will do for sloppy quorum and later hint off and bring back the data to these.
Correct. Because that makes sense actually. Because suddenly now I won't have an overlap because
that was my.
That makes sense.
But when you write the data to a node outside your cluster, does when it do the read, does all the node have to know that there's one node outside cluster holding the data?
No, exactly. So when you do a read, it won't actually ideally go to that outside node, right? And that is where it's saying that, so this is where I'm saying that when a read is issued, let's say it goes to one of the nodes in my, which hasn't recovered, then it will be a problem. Right? That is the whole idea of sloppy quorum, that it won't satisfy the consistent read property, right? It won't always give you the latest data.
Yeah, so your read will be stale in this case.
Yeah.
But if a node is
so basically, are you saying that the node that went down, it came back up and hasn't taken that, the updated data yet, and that's when the read comes in?
Yeah, it can be at different stages, right? Either it hasn't, been updated with latest data, or anything that happens between this lag time, right, before B recovers fully, right, when B is available for it. Actually, I might be a little confusing here because I'm setting it to a node, right, where we have been talking about numbers. So I might be a little confusing here. So maybe
Yeah, my idea was every time, if like, throughout this whole session, right, or even the previous replication session, if a node goes down, even for little bit of time and until it's recovered, I don't know if it's a good node to be kind of, getting read from. So
right, so those are the properties about, I was going to cover in like anti-entropy, like read, repair and stuff, because you don't want to keep, the stale thing. You want to make sure that, you're reading the right data. Yeah, so that is an approach that is followed to ensure that. Um,
So here I'm not understanding one thing. If we are writing to A, B, and C, then why we are calling them as replicas? I mean, what is a replicas for write operation means? The
so I
replica
mean
is
to say,
basically something that mirrors the original
right, maybe
operation,
I
right?
was confusing. So I meant to say that these are the right quorum sort of, right quorum set.
And if you take a look at the slide number 6, I mean, there is no mention of replication, whereas in the slide 6, we are saying that the writes go to all the nodes and reads go to all the nodes. And
Yes.
we just make sure between whether to read it, we need to agreement of the value between 3 nodes or 5 nodes or 2 nodes.
No,
That's
we are not
the move
looking
now,
at
right?
agreement of values, but we are looking at how many nodes that we hear back from.
Okay.
So like if you look at agreement of values, that's not happening here, right? For example, you're sending to all, but one node is having a different value. So agreement is different. That is where the idea of stale and latest value comes in. But what this slide is saying is that how many nodes should I wait to hear back from to confirm to the client that write or read was successful?
One question I
Yeah.
have is like, by this, we are pushing the responsibility of replication to the clients, right?
Not the replication, but the consistency, like how do tunable consistency. Why do you think the responsibility of replication?
Because now the client has to send to all the nodes where the data needs to be replicated, right? In other cases where we just send to the leader.
Can we go on?
Naga, it doesn't have to be actually client itself. I mean, if you have attended that Cassandra session, so the write itself can be forwarded from the client to a coordinator, and the coordinator takes care of writing it to the corresponding replicas.
Okay, so we still have a coordinator which is acting as a.
Yeah, it is possible to interface here.
Yeah, it can be either ways. I mean, but if the client has to write, it has to know the other nodes as well. There might be, I mean, you might have to contact some other points to some other endpoint to get all the nodes in the cluster and these all. Both are possible.
Yeah.
Depends.
So so Naga, I think one thing I would say on your question is client is not responsible for replicating per se, but yes, you're right that client, first of all, has to forward the request to X number of, nodes, but client is responsible more for triggering, that things are, let's say, out of sync. That is what client triggers. And then the system, there might be other components which take care of, syncing the replicas and all that. But it's not specifically that the client component has to deal with this burden.
But if we treat that as a client, let's say, we treat it as a client, then, they have to know, right? When the node goes down, or when, we choose a node outside replica, that's one need to know.
Right. So that is where I think, yeah, you're right. I mean, that kind of logic has to be added, that how do you, if node is down, how do you reach a node outside the replica set and stuff.
And similarly, like to get the latest version also, I think it's better to always have a coordinator, because who will have all the logic that pick the latest version out of these 3 nodes?
Yeah.
But you know, looking at this diagram where we were saying like n is the number of nodes in the cluster, it doesn't look like that. N is your replication factor.
Yeah, I mean, I think I should.
You never go out of replication factor at all. Like, what's the point? How will the other readers find it? Where is your data, right?
Right. So this was actually, I think I learned something I wasn't going with. I was thinking of it as number of nodes in the cluster, but this is actually the replication factor.
And if we take n as a replication factor, then whatever Cassandra example we discussed, then it all makes sense, right?
Right. Yeah.
It's just one thing, you know, when you said about a coordinator. So when there is a coordinator, doesn't it mean that it's going to be another sort of a leader there?
Yeah, I felt the same.
Yeah, you know, so therefore it's like a hybrid of a leaderless plus leader, something like that.
Well, yeah, it kinds of, that's a good point. So I think one way to think about this is leaderless, we are talking in terms of the actual, like the node structure, right? Coordinator, can we think of it more on the client side? But
so no, I think it's different. It's not a leader, because there will be multiple copy of coordinators and they have the same logic. Like they will have just lightweight logic that, hey, these are the number of nodes. I want to forward the request to these nodes for this data, and I want to pick this latest version. And that same code, the code logic will be deployed on multiple coordinators, so that your coordinators have a single point of failure and your requests are divided among multiple coordinators. But as a such, coordinator is not a leader. Like
yeah,
it's
like when
just
you
a lightweight, like a load balancer kind of thing.
Correct.
Oh,
And when we think of leader in this context, we are thinking of leader as a node or a set of nodes which can actually serve your read and write request, right? Which is very different from, like Abhishek is explaining, that coordinator is more like load balancer, and we can have this, you know, failover, you know, mechanisms and multiple coordinators.
yeah, makes sense. Maybe like a distributed systems coordinated services, Zookeeper, something like that. Or maybe, yeah.
So the functionality, the responsibility factor is very different.
Yeah.
What we are calling for leader.
Yeah, thank you.
I think having a coordinator in this multi-leader case makes sense, because without that, because client maintains
you jump to another
connections and having the knowledge of scale outs and all these things is doesn't look practical. Yeah,
makes sense.
I just want to clarify, when you say healthy node, what does it mean? Like, if can the data be out of sync, or it should be the data should be consistent with the, you know?
So I am thinking of healthy node as data possibly won't be in sync, right? Because if we are jumping out of a replication cluster, right, out of 100 nodes, let's say I have 5 nodes as my replication, and I'm jumping to a node outside this. That node may not have the same data as these, right? So it won't be in sync, but it's functioning, like it can accept request from the client. That's what I mean by healthy node.
So it can potentially be like a new node totally with no data.
Sure, if it's, you know, it's a part of the cluster, it can be that. It's something that can be a temporary, you know, serve your read and write request. But of course, if you're talking about read request, you have to be careful about that. It won't be consistent, right? You may get response that data is not present. But in case of write, you are just borrowing that node because it's working fine, and you're just taking it as a temporary placeholder for your data until the original node in the replica set comes back. That's what I think.
Okay.
Yeah. But good discussion. I think I learned, got some clarifications there. So going back to this idea, the main point was, if you do not have the number of nodes that are required to satisfy your right quorum in your replication set. Then you jump off to a healthy node, functioning node outside your replica set. You use it as a temporary placeholder, but you put some flag there called a hint that tells it that, okay, which node does it need to talk to when that failed node comes back. So B recovers and D talks to B and things come back in the right quorum set. Yeah, so that was that. And then, so this is where we were. So I was saying that this equation, even though you start with this equation, but because of the real-time systems, network failures, there may be a situation where you slip into this sloppy quorum.
Just thinking about it, like, with the help of coordinator, maybe we can, avoid this sloppy quorum, right? So, like if any of the node hasn't picked up all its hint, then it should not issue a read request or satisfy a read request. Could that be something we can use?
So
but we wanted to satisfy the read request, right? So to guarantee the high availability. So that's why we have to borrow a node outside of the replication, that quorum.
I didn't get the earlier idea where you were suggesting that how can we avoid this using
So like we should not be picking any node to satisfy a read request which hasn't picked up its hint, right? Then that means the data is out of sync and it's not updated yet.
Exactly. So that was the one approach that we said, right? If let's say you can't satisfy your write quorum or read quorum, one way to deal with this is respond to the client that it can't be, respond with an error or something, right? That is what you're suggesting. And then you don't land into this, kind of situation. This is like, I don't know if I was mentioning this here. Yeah, I add it here, but you are right. I mean, that is one way to deal with it. That if you can't satisfy that quorum, you can respond by, saying that either retry or something. But if you want to avoid that, for example, especially for writes, right, you don't want to totally ignore it, then this is an second approach. Yeah. So it can be avoided, but you have to just define what your application is okay with. Is it okay to receive that it can't do something, or you're doing something at the expense of, trading off something else? Yeah. So
yeah, if we wanted high availability, right, then we want to go for that sloppy quorum. I mean, not like we want the high performance kind of.
Yeah, like if you
is high availability, when you say high availability, does it mean that it will just return response and it can be a wrong or stale response? How do you
So availability is an overloaded term, right? It depends on how you say. Do you say, well, you're right, like availability is like, do I say that I'm going to serve the request at the cost of something else? So I don't see the sloppy quorum as availability thing. It's more
No, I mean like to get the response back, to get the work done, right?
Yeah,
if you want to get the work done, then you use it sloppy quorum.
Yeah. So
or if you don't, you just retry or deny it.
Right, rather than getting a retry or deny message. So that is
that means high availability, right? So
yeah,
sloppy quorum is for high availability and eventual consistency. That if you have sent me some data, I'm storing your data somewhere. Although if you read it, you will not get this latest data right now, but some point in time when things eventually become consistent, then I will give your data. Your data is not lost. I have it with me and your system is available. It's only that you might get some stale data for some time.
Yes. So, okay, I wanted to cover this, the second idea, but I think I'm just going to mention quick, we are already on time, but maybe we can take this one and the version vectors and concurrent writes then later. But so just to wrap things up, so we actually started from this point where we said, in this situation, we have two branches to look at. One is the quorum concept, which we covered. The other thing is, how do you actually detect inconsistencies in your replicas and how do you fix them? That is where I wanted to talk about different approaches. So some are like background and foreground. So we can take that up next time. But yeah. So I think we'll stop here. Any